The relationship between KEQ and the standard cell potential? Well, if delta G is equal to negative NF times the cell potential, then delta G naught, okay, the standard Gibbs energy for a reaction would be equal to negative N times F times the standard cell potential. Now, if you remember from our discussion of the second and third law, we said that delta G is equal to delta G naught plus RT ln Q. That's why your cell potential depends on your Q. Remember we said? Okay, so if you were to make the substitutions here, okay, so delta G is negative NF E cell is equal to delta G naught, which is negative NF E naught cell, plus RT ln of Q, okay? And you divide both sides by a negative NF. That gives you, that NF cancels. That gives you this equation right here, which is called the Nernst equation. The cell potential is equal to the standard cell potential minus, okay, there's a minus there, NF minus RT over NF times natural log of Q. This is called the Nernst equation. This tells you how the cell potential depends on your reaction quotient. What happens to your reaction quotient as the reaction progresses? Eventually, it's going to approach your KEQ, right? All reactions eventually approach KEQ, the reaction quotient. And so, what do we know when it's approached KEQ? Delta G is going to approach 0, right? And your cell potential is going to approach 0. At equilibrium, when your battery is fully discharged, it's not going to put out any voltage, right? So delta G approaches 0, cell potential approaches 0. So we say when the cell potential is 0, that's going to be equal to E naught cell minus RT over NF natural log. And instead of plugging in Q here, we now, actually we do plug in Q here, but the Q is now going to be equal to KEQ. So at equilibrium, we say that 0 is equal to E naught cell minus RT over NF natural log of KEQ. Okay, so if you have a way of measuring the standard cell potential, that will tell you what the equilibrium constant is. So this is one way you can determine the equilibrium constant for a reaction, for a redox reaction. You figure out the standard cell potential. You find a way to measure the standard cell potential. So how would I solve for KEQ if I know my standard cell potential? How would I rearrange this equation? I can say then that E naught cell equals RT over NF natural log of KEQ. And so I can solve for KEQ. It's going to be NF E naught cell over RT. I'm just going to rearrange this. I'm going to move this over there and move this down here. This natural log of KEQ. And then I just take the anti-log of this to get my actual KEQ, right? So KEQ would be E to the negative NF E naught cell, positive NF E naught cell over RT. Okay. Was there a negative? Oh, see when I move this thing over to the other side, this one, if I move this one over to the other side, it becomes positive. Okay. Or, remember you also said that instead of ln k, you can use base 10 logs. Okay, the alternative form of your Nernst equation, what was it? Here's a math review. Ln of k would be equal to 2.303 base 10 log of k. Okay. So if you take base 10 log, you multiply by 2.303, that gives you natural log. So if you combine that, so this is going to be E naught, this thing right here, instead of that being that, you can say that's the same thing as 0.059 over n times base 10 log of q. All right. In this case, you factor in your 2.303 and then change it to base 10 log. Okay, and we're plugging in 298 Kelvin as our temperature, 0.0592 to be more precise. Okay. All right. So that's how you can calculate. Okay. So let's do some calculations. Let's calculate the reduction, KEQ, for the reduction of iodide by ferric ions. Okay, and then we do the same thing for the reduction of bromide by ferric ions. So if I want to reduce iodide, what should I do? I'm sorry, this should be oxidation. Okay, but, fix that, please. So I want to oxidize iodide. So what I look up the standard reduction potential of I2. It's that. Okay, and iron is this one. Okay, you have your iron can be reduced to Fe plus 2. Okay, so if it's reduced, it can cause something else to get oxidized. So let's say you want it to oxidize iodine. Okay, so what's the oxidation reaction then? I have to flip this one, right? Flip this to make it an oxidation. I say 2 iodide aqueous yields I2 solid. And I'm just going to leave out the physical stage to make things easier to follow. Plus 2 electrons. So what's my cell potential for this one? Oxidation. So oxidation potential is going to be negative 0.53. If you're wondering where I found this, I look it up. Okay. Now, what happens when you do iron? You still have your iron for your reduction. Iron plus 3 plus electron gives you iron plus 2. And the standard reduction potential for that is 0.77. Okay? So what do I need to do to get the overall reaction? To get the balanced overall reaction, what should I do? Electrons lost must equal electrons gained. So what should I have to do with this second step? I have to multiply that by 2. Keep in mind, standard reduction potentials are intensive properties. Even if you multiply your coefficients by 2, the potential remains the same. Okay, so you don't multiply this other side by 2. So if you combine these, you have 2 iodide plus 2 ferric ions, Fe plus 3, yields I2 plus 2 iron plus 2. That's your overall reaction. That's a redox reaction. And what is your standard cell potential here? It's going to be E naught oxidation plus E naught reduction. So negative 0.53 plus 0.77, that would be how much? 0.24. Okay, that's E naught, right? What's my KEQ? E to the n f E naught over RT, right? So that's going to be equal to E, I can say EXP. That's another way of saying E. And what's our N here? How many moles of electrons are transferred in this reaction? N is 2, right? 2 moles. Okay. And Faraday is 96,500. We're going to put everything in SI here. So our standard cell potential is 0.24 volts. Divided by R, we have to use 8.314 joules per mole per Kelvin. And temperature is 298 Kelvin. Okay. And let me just leave out the units to make things easier to follow. So what would that be? 2 times 96,500 times 0.24 divided by 8.314 divided by 298. That gives me 18.70. Okay. So this is e to the 18.70. What would that mean? If I do this, I have to take inverse log, so inverse and then e to the x right here. That gives me 1, 2, 3, 4, 5, 6, 7, 8. 1.3 times 10 to the 8.
Why did you use the positive 0.24?
Why did I use the positive 0.24? It is positive. Yeah, it is positive. Negative 0.53 plus 0.77. Okay, so this is, okay. Oh, this thing right here, f to e, that's fixed notation to exponential notation. That allows you to switch between the two. So this is 1.3 times 10 to the 8. Okay, so 1.3 times 10 to the 8. Now, is that a large or a small equilibrium constant? Large KEQ. That means products are favored at equilibrium. This is a reaction that you'd expect to go almost all the way to completion. Okay? So a positive cell potential means it will go far, right? Far towards the product side. In fact, you can relate that to delta G naught. Delta G naught is negative NF E naught cell, right? So the more positive this one is, the more negative the delta G naught is. Remember we said a very negative delta G naught is a reaction that goes far towards the product side. Okay, so the more positive the standard cell potential is, the larger the equilibrium constant. What would be your equilibrium constant if the standard cell potential is 0? E to the 0 is 1. Okay, that would be your equilibrium constant. What if it's negative? E to a negative number would be a number less than 1, so your reaction is not going to go far. So if you have a negative standard cell potential, you're looking at an equilibrium constant that is very small. Okay, so let's try the other case. This time let's do bromide. Instead of 0.53, we're going to use 1.07. So our oxidation potential for bromide this time is going to be so you're going to do 2 bromide yields Br2 liquid plus 2 electrons. The oxidation potential for this is negative 1.07. Okay, so when you add up the two, what do you get? So instead of iodide here, you're going to have 2 bromides. And instead of I2 over here, you're going to have Br2. What do you see here? What's our cell potential this time? We're going to have negative 1.07 plus 0.77. What would that be? Okay, so 1.77 minus, okay, 0.77 minus 1.07, that's negative 0.3. Okay? So that means, this is involved, that means what? This reaction this time is not going to go far forward. It has a negative cell potential, and so delta G here is going to be positive. So what would that be? If I plug in, instead of 0.24, I plug in negative 0.3 over here, what would I get? Let's try that. 2 times 96,500 times 0.3 divided by 8.314 divided by 298. That gives you negative 23.37. Okay, so e to the negative 23.37, inverse log, make that negative. Okay. Inverse log. That's 7.09 times 10 to the negative 11. That's a very small KEQ. What's one practical application of this in the lab? If you have a mixture of iodide and bromide, and in Chem 110 you'll be doing this experiment, if you have a mixture of iodide and bromide, you add ferric ions to it. Okay, you can separate the iodide from the bromide because the iodide will react. It will give you I2, and then the bromide will not. And then what you can do with the I2 is, what you do in the lab is once you form your I2, okay, so you have your I2 now and your bromide, right? Your bromide stays the same. It doesn't react very well with ferric ions. Your iodide will give you I2. So what you can do is you can add a nonpolar solvent to that, like hexane or carbon tetrachloride. Your nonpolar I2, okay, will be selectively extracted from your mixture. Okay, a nonpolar solvent will preferentially dissolve I2, and so you can remove it and you can have it separated from your bromide. And you can sort of tell from here, okay? Remember, the reverse of this would be negative 0.53, and the reverse of this would be negative 1.07. You say that iodide is has a greater tendency to get oxidized than bromide, right? Iodide is more likely, has a greater tendency to lose electrons than bromide because it's got a less negative oxidation potential.